Okay, so uh, let's get started. So I cannot use the mic. So we learned about the branch prediction and exceptions in the previous class, right? So actually, in the using branch prediction, so we can predict the future result of the branch instructions. So you need to understand how the branch predictor works, right? And then also branch predictor is in the instruction fetch stage, right? So using PC, a program counter, we can identify branch instructions, and then we can access the branch prediction buffer, right? So by accessing the branch prediction buffer, we can predict the future result of this branch instruction, right? Also, I explained that the target of the branch instruction, the target of the branch instruction is a kind of constant value, right? So we can just store the, the target of the branch instruction in the branch target buffer. Also, we can access the branch target buffer using program counter, right? So you know the branch prediction buffer and then branch target buffer are in the instruction fetch stage. Okay? Then we learned about the exceptions. So I explained that exceptions need to be supported by processors, right? So in order to support the exceptions, well, if when the exception is detected, then the processor stores the program counter and the causes of exceptions, right? And then also you need to understand how the instructions are handled in the pipelines, right? So when exception is detected, the instructions, the previous instructions need to be completed, right? And then the current instruction that encounters an exception and following instructions need to be flushed, right? It's cancelled. Okay, that's what we learned in the previous class. Also, the exception is to be handled the order of instruction, not in the order of the detection time, right? So it's also important. Okay, so the instruction order means that so actually the processor employs the pipeline architecture. So which means that if an exception is encountered in the instruction fetch stage, right? So it can be detected in the instruction fetch stage. But if the also the exception can be detected in the memory stage, for example, but the later, okay, after this exception is detected. So in this case, what is the instruction order? So what is the earlier instruction? Instruction is the memory stage, right? So which means instruction order means the instruction the is memory stage is to be handled first, right? So in this case, so even though this exception is detected earlier, so it can be possible because this is the instruction fetch stage, right? But the later the exception can be detected in the memory stage in the different instruction, right? In this case, this exception need to be handled first, right? So it's so so in order to so this is called the precise exception. So there is the multiple exceptions. So we can find the precise exceptions. So precise exceptions means the exceptions are handled in the order of instruction, not the exception detection time, right? So in order to support the precise exceptions, the exceptions are handled when the instruction reaches right backstage usually. Okay, but in the processor, so actually if you can take the advanced course of the computer architecture. So if you are a graduate student, right? Then actually the modern processors employ out of the processor architecture. So we are learning about the in order processor, and then actually this is very simple process architecture. But most CPUs employ out of the process architecture, right? So in order to support the precise exception, the out of the processor, the exceptions are handled when an instruction reaches in right backstage. Okay? So that's how the exceptions are supported. Okay, so precise exception represent the exceptions are handled in the order of instruction, right? Okay. And then also the processor can support imprecise exceptions. Okay, so but it's very complex. So actually the precise exception, so, it is usually required that a CPU supports precise exceptions, but sometimes the CPUs cannot support precise exceptions. So, and then this case is called the imprecise exceptions. So imprecise exceptions mean the exceptions are not handled in the order of instruction, right? Then it is called the imprecise exception. But in this case, the exceptions also need to be handled. Okay, so actually the exceptions are handled software manner, right, by operating systems, the imprecise exception, right? So this is the exception. Okay, then as I mentioned, the last question of the homework 3 is regarding exceptions. Okay, and then you can I hope you can understand how exceptions are handled in the pipeline architecture. Okay, so we are ending the pipeline architecture, and then before moving on next chapter, so I will briefly explain about the simulators. Okay, so computer architecture tools. So we are learning about the computer architecture, right? The architecture layer of the computer systems. Okay, so if you are working on the computer architecture, then we may need to add, we may need to implement our idea, the architecture of a computer system, right? Then how can we implement our idea on software? We can just write the code, right? Then we can just compile the code, then we can execute our compiled code. Then we can implement our ideas on software. So it's easy and simple, right? Then how about the architecture? So architecture includes the software part and then hardware part, right? The software part is software part we can implement our code. We can write our code and we can compile our code, right? How about the hardware part? The hardware is a hardware, right? So hard. So So we cannot modify the most cases we cannot modify computer hardware. Then how can we work on the computer architecture research? We can use simulators, okay? Which means we can use a software that emulates the behaviors of computer hardware. Okay? So emulation. So what is emulate? Emulate means imitate, right? Imitate the behaviors of the hardware architecture, right? So we can use the software, then we can modify this software like the simulator, then we can just implement our ideas. So it can be possible. So we can just use the real hardware like this. Okay. So if you see this photo, so actually this is the real photo I worked on. Okay. So I used this hardware for my research, right? So what can you see? So you can find. So actually, so this is the real hardware board, right? Then so this board includes the FPGA, it's the programmable chip. So we can also use real hardware, but problem is difficult, right? It's difficult to use. So the software debugging is much easier than the hardware debugging, right? So for the hardware debugging, so we need to capture the real hardware signals, right? Then we need to verify the waveform signals from hardware, right? So it's not easy, right? So usually for computer architecture research, so we can use simulators, right? Software, and then these simulators emulate the behaviors of computer hardware. So it's a software. So actually, we used the kind of simulator, but for our lab, Spike, right? So Spike is RISC-V ISA simulator, right? So using Spike, we can execute the binary file compiled for RISC-V ISA, right? So actually, the commodity computers like the Intel computers, like actually on Intel CPUs or Apple CPUs, we cannot run RISC-V binaries, right? But if we use the Spike, then we can run RISC-V binaries. But Spike is just a software application. So which means the Spike just reads the RISC-V binary, then Spike just emulate the behavior of RISC-V instructions. So I just define this processor model, the instruction is given. Then what is changed? What are changed? Register file and the memory. So Spike, the RISC-V ISA simulator, reads the RISC-V instructions from binary file, right? And then it just modifies the software model of register file and memory, right? So it's a software. So using the Spike, we can execute RISC-V instructions. Also, we can verify our RISC-V binaries, right? This is software. So even though we do not have we do not have the real RISC-V processors, the Spike can execute. Spike can emulate the behavior of RISC-V processor. So this is the simulator. so we can use simulator for the architecture research. Actually, but there are any kinds of the RISC-V assembly simulators. Jupyter, Glass, and so famous across the RISC-V. So it is because the RISC-V is the open source ISA. It's not commercial ISA like ARM or x86. So the academia we can develop any simulator. So any assembly simulators for RISC-V, and then those simulators are open source software, right? So, which means there are many RISC-V simulators. So actually, these are RISC-V assembly simulators. So which means even though we do not have a real RISC-V processor using these RISC-V assembly simulators, we can execute RISC-V binaries or RISC-V assembly code. Okay, then these simulators just shows the changes of register file and memory, right? Because you need to remember that is the execution model. The instruction is executed, then register file and memory are changing. So simulator just implement these behaviors using software. So this is the example, it's a screenshot of the Jupyter. The Jupyter RISC-V assembly simulator. So you can find this code, the machine code here. So you can find the contents of register file. Right. So based on the based on the RISC-V ISA documents, the RISC-V ISA specification, these simulators just change is register file content, but it's a software. It's a software data structure. Okay. Also, this is Jupyter. Then also there is a graphical architecture simulator for the Y. So this is, I think this is very useful tool, right? So actually, I showed the architecture of the 5-stage pipeline RISC-V CPU, right? And then actually this simulator, the right simulator, can show the instruction flows. Then the contents of the database element of this RISC-V 5-stage pipeline architecture. And then it's a graphical tool. Okay? So if you use these tools, you can understand. I believe you can easily understand how the instructions are executed, and then how the instructions change the content of the database element. Right? So I think this is very useful tool. So I believe you can use this right tool for understanding the behavior of the 5-stage RISC-V pipeline processor, right? Also, the last design name will be posted on November 27, right? And then for the fifth lab assignment, so you will be requested to design the pipeline architecture, the 5-stage pipeline architecture. Then you can get help from this white simulator. Okay, so you can just see how instructions flow each pipeline stages. right? Also, you can find the content of a register file. Yeah, also this the instruction this is the instruction memory. So you can also check the content of the memory and register file using this simulator. But the problem is sometimes uh, the simulator has bugs, right? So this is the open source software, so it's not supported by commercial companies, right? So sometimes, so it's actually these tools are developed by the academic communities or as a personally. So some tools have bugs. Okay. And then I also found a bug of the drive. Okay. So so please be cautious about the bugs. Bugs of this tool. Okay. So actually you are learning about the hardware architecture from the very basic simple, but it's fundamental the process architecture in this course. So try to understand the real behavior. Behavior of is pipeline architecture. Okay, you can get help from some source. Okay. So actually, for hardware research, so if you are interested in hardware research or architecture research, so it is required for emulating. It is required to emulate the hardware behaviors into software, right? Sometimes, so it's not easy because for software, so we can, as I mentioned, we can just write the code, right? Like some normal languages. So the code, the program language syntaxes are similar to our high-level languages, our natural languages, right? So for the software development, we can just write the code like using normal high-level languages, right? And then we can just compile. And then compiler will report the warnings or errors, right? And we can just fix our code. Then also we can debug our code, right? So it's simple. Then it's uh, it's convenient, right? But the hardware, so you need to understand that hardware is the real, so it's the machine that works, the real world, right? The software works in the virtual world, right? Actually, right? The fantasy world, but hardware works in the real world. So when you emulate the real behavior of the hardware, then you need to also consider some constraints where the real behavior of hardware. Then you need uh, you need emulate. You need write a code that can describe the real behavior of hardware. So both the hardware research, this is required. Okay, so sometimes it's different. So software, we can just it can be similar, but because for the software development, we can just emulate our thought, right? Our thinking. But in the hardware, so hardware research, we can just write the code that can emulate the behavior, the real behavior of hardware. Okay, so this is required for hardware research. Okay, so and then these tools can be helpful for understanding some behavior of hardware. Okay, so try to use this tool. we will move on the next the new chapter of this course, the memory hierarchy. So I mentioned that the ISA and then the pipeline architecture, the process architecture, and memory hierarchy. Those are very important topics in this course, right? So that's important topic. So we will learn about the memory systems in a computer system, right? So what is a memory? So we can store. So in chapter 2, we learned about the memory instructions, right? What are memory instructions? Load and store instructions. Then what are behaviors of memory instructions? The load instructions transfer data from memory to register file, and store instruction is the inverse of the load instruction. Store instructions transfer data from register file to memory. Then why is memory required in the computer systems? We store our data, then we store instructions in the memory, and then processors read and write data or instructions in the memory, right? So we can store any data. Then also instructions are data, right? We can store any data in the memory. Then the processor reads this data from the memory, and then processors can execute the instructions, or processors can process our data. So then where is the memory? The computer system. So this is the photo of the main board of the old computer systems, right? I mentioned that the CPU is here, right? So where is the memory? Memory is here, right? So desktop CPU or server, desktop computer or server computer, so we can just use memory DIMMs, right? Like it's called the DIMM. And then we can just insert memory DIMMs in the memory slot. The memory slot of the computer board. Okay? The CPU is here. So what can you observe? Memory is located outside of CPU, right? In the real computer system, right? Step us. But in chapter 4, in the process architecture, so we learned about the 5-stage pipeline architecture. Then where are memories? The memories are here and here. So this is the instruction memory, and then this is the data memory. So actually we learned about the memory. But you can observe it's different. Real computer system, the memories are like DRAMs, like DRAM memories. The memories are outside of the CPU. But in chapter 4, we learned, memory is in the instruction fetch stage. So the instruction, this is the instruction memory. And then data memory is in the memory stage. Right? So it's different, right? Right. Because a computer system employs multiple levels of memory systems. And then these multiple levels of memory system are called, this is called the memory hierarchy, right? So Actually, so this is the memory hierarchy model. So which means in a computer system, there are different levels, which means different types of memories. Okay, so actually we learned about the very simple model. So in chapter 2, we learned about this model. So this is the processor, then so instruction is given, then the instruction, the processor can change the two types of memories, like that is the file and main memory, right? This is the programming, the instruction execution model we learned in this course, right? So, and then, the register file is here. So actually for the memory, you can just understand this computer system that includes the memory system like this figure. So what can you see? You can see the processor, right? And then you can find the memory. So, and then actually the processor needs to read data and instruction from the memory. And then also processor needs to store data and data, the memory, right? So in order to access the data in the memory, what are required? Addresses, right? Then in order to write the data, then write data is required. So you can find, so we already implement the data memory, right? So what are required ports for this data memory? We implement the address port, then we implement the data in, right? Then also we implement the data out, the data memory. So you can also in the data memory, the data memory has a control port, right? So like the mem write or mem read, then clock signal. So you can find this model. The processor provides the control signal, addresses, then write data, the data in. And then the memory can store. So processor can provide the address, then the data can be read from the memory. So, and then, so processor accesses data in the memory. So we can say that the performance of this model, so like the processor and memory, so the performance of an entire computer system can be influenced by performance of a processor. That's what we learned in the chapter 4, right? So we need to improve the performance of a processor. But when we mention the performance of a processor, we just assume that memory performance is just it's very fast. The memory is very fast, right? So it means so we can read the data, we can read instructions from the instruction memory within one clock, right? So we also assume that a processor can read data from the data memory within one clock, right? But actually it's not true. Okay? So because the processor needs to read data from the memory, and performance is also influenced by the performance of memory system. Okay, so you can understand the performance of a computer system is highly influenced by the memory system, the performance of memory system. Okay, because you can just understand the processor model like this. But problem, what's the problem? So as I mentioned, we just assume that the memory is very, very fast. But actually, it's not true. So you can find this graph, okay? The y-axis is the performance, and then you can find that this is the log scale, and then also this is the year, the time. So you can find that the CPU performance is increased exponentially. The memory performance is also increased so exponentially, but you can find that the performance of CPU is increased high. So you can find the performance gap between the CPU and memory. So what does that mean? So performance gap is increasing. So actually, memory is slow. CPUs are very, very fast. So you can just observe that CPU clock frequency is around the 3 gigahertz or 5 gigahertz recently, but memory is slow compared to the CPU. So it is because the semiconductor technology. So semiconductor technology for CPU and memory are different. Also, so there are many factors that determine the performance of the memory. But the memory manufacturing is a little bit different from the CPU technology. So the memory is slow. Okay. So the gap is increasing. So what does that mean? So this is a system that composed of processor part, processing part, then memory part. And then one of the part is slow. What's the problem? Slower part dominates the performance of system. Right? It's the same to the real world. Slower part dominate the performance. Right? So the performance of memory, because the memory is slower than CPU, the performance of memory becomes a bottleneck, performance bottleneck of a computer system. And then this graph shows that the performance gap is increasing. And then recently, so actually you can find the year is the 2005, which means actually the performance, CPU performance is saturating. Then the memory performance is likely increasing. So this gap is decreasing. But anyway, you can observe the huge performance gap between processor and memory, right? So memory is slow. You can just understand that, oh, memory is slow, right? And then this is the problem. This is critical performance problems in computer system. And then this gap, the performance gap between the CPU and memory is called the memory wall. Okay, so this is a very popular term in the computer architecture, right? Actually, because it is because this performance gap, because of the performance gap between the CPU and memories, the performance of the entire computer system is dominated by memory performance. Okay? It will slow down. So many researchers are focusing on the performance of memory systems. Then it is still very critical. Why? AI models. So modern AI models such as the GPT-4, actually these models require huge amount of parameters, right? Parameter data. Then this parameter data size is very, very large. So actually, because the data size is very large, so the performance of memory, the performance memory is critical for the performance of AI systems, right? So still the memory system is very, very critical, right? Then, this is called the AI memory wall, right? Then it's a little bit different. The AI memory will just represent the size problem, the size issues, size of data of the modern AI models. But anyway, the memory system dominates the performance of a memory dominates the performance of entire computer systems. So that's the problem. And we need to improve, we need to handle these issues, right? How? So in order to handle these issues, we can use the memory hierarchy. But so memory hierarchy represent that. So this is the register file. Then these are caches. These are cache memories. Then this is the main memory. Then this is the storage. So we already know about the register file. So what are unique characteristics of register file? So I mentioned that the register file. So there are only 32 entries or 32 elements the register file. So which means it's very, very small. But it's fast. Instructions can store data in the register file first, right? So we can just update the register file data using instructions. But the size is very small. So we did not learn about the cache, but cache is the temporary memory in the processor. And then actually the cache size is also small, but it's fast. But the cache is slower than the register file, right? But it's relatively fast. Relatively, so what does that mean? You can find the main memory here, the DRAM. So DRAM is relatively large, but it's slow. So in a computer system, so we frequently mention that size of this computer system, the size of the memory in this computer system is 4 gigabyte, 8 gigabyte, 16 gigabyte. It mentions actually the size of the RAM. So actually we did not learn about the cache yet, but you can just understand that the DRAM size is larger than the register file. But when we compare the size and then the performance of this main memory and cache, the cache size is smaller, then caches are faster. Then also there is storage. There is a storage system such as SSD and hard disk drives. Then you can store our data in this SSD and hard disk drive because size is much larger. So compared to the DRAM, the size is much larger, but it's slow, right? So what can you observe? So in a computer system, there are different types of memories, and then actually different levels of memory. Then we organize the different types of memories. Memories like this hierarchy. There is a processor. Processor is here. right? The top of the hierarchy. So what can we observe? So we can observe that in the memory hierarchy, this hierarchy, the, the the higher level of this memory hierarchy includes the fast memory, right? Then but the size is small. If the hierarchy level is low, like the storage, the size is large, but it's very slow. Then why do we need the fast memory? Because like this model, the performance of a memory system determines the performance of entire computer system. What's the problem? Now to increase the performance of a memory system, we need to use the very small memory. That's the problem. That's the dilemma. That's the dilemma of the memory system. We want to store large amount of data in the memory. But if we just use large memory, then this memory is very slow, right? So, in order to increase the performance of the memory, then we can just reduce the size of the memory. What's the problem? We can reduce the size of the memory. Then problem is that we can just store the small amount of data in the memory. But we can just handle large amount of data, right? But then the data size is increasing. So that's the dilemma. It's the dilemma of the memory system, right? So we can just organize the memory system like this. And why? We can observe the locality of data. So you need to understand the locality of data. Okay, so actually the processor reads data from the memory. So which means that if we want to use the fast memory, so which means the data can be, if the data is found in the fast memory, then we can increase the performance, right? So then you can think like this. If data is frequently found in the smaller memory, then we can increase the performance, right? If we use a certain data infrequently, then this data can be found in the slow memory. So if we use a certain data frequently, and if we just locate this data in the fast memory, but this data, the memory size is small, right? So we can just store the frequently used data in the small memory, but the performance is high. So which means that this memory performance is high. So we can increase the performance, right? This is the main idea. So if data is frequently used, then if data will be in fast memory, but its memory size is small, but the very data is infrequently used, then data can be the slow memory, but this is large. This is the main idea. It's the same for the real world, right? In the real world, if we use a certain device frequently, like the smartphone, right? We frequently use the smartphone. Then it means that we can also access smartphone from our pocket, right? It's a near it's close to me, right? Close to us, right? Smartphone is near, is close to our body. How about the any some books or textbooks, some other materials? It's far from us because we we do not use these books or materials in frequently, right? It's the same because we use smartphone frequently. The smartphone is close to us, and we can quickly access smartphone. It's the same. A processor uses a certain data frequently, then we can just locate its data in the fast memory, right? Then if the data is used infrequently, then we can just locate this data in the slow memory. So this is the main idea of memory hierarchy. So then how can we figure out the frequency of the data usage? So which means that how can we determine a certain data is accessed frequently? So we can observe the locality of data, like and then there are two types of locality, like the temporal locality and spatial locality. So what is the locality? So locality means that it's if we just access a certain point, then actually we can just measure some distance, like the distance from a certain point, right? And then if the distance is close to a certain point, we can say that, oh, this is the locality, right? And then there are two types of locality, like the temporal locality and spatial locality. So which means that we can just measure the distance from a certain point in a time manner, or distance, like real distance, right? The data is the same. The temporal locality means that, oh, our program access a certain data, right? A certain variable, like a variable I. Then this variable will be accessed again in the near future. This is called the temporal locality. So what are examples of temporal locality in a computer system? Instructions in a loop. So for example, you can find the for loop here, right? And then so inside the for loop, there can be multiple statements. So these are instructions. So what can you observe? Inside of the iterative loop, if these instructions are accessed, then these instructions will be accessed again and again, right? So this is the example of temporal locality. So I mentioned that the instructions are also data, right? Data in the memory. So certain instructions are accessed once, then these instructions will be accessed again and again. This is the temporal locality. Also, some variables such as the index of an array. These variables are repeatedly accessed by programs, right? So this is the example of temporal locality. Temporal locality means that certain data is accessed once, then the same data will be accessed again in the near future. Okay? Then spatial locality. So spatial locality means that if a certain data is accessed, then the neighbor data will be accessed in the near future. So it's a closed data. So this is called the spatial locality. So what is the example of, what is an example of spatial locality? Array data. Like if the A0 is accessed, then we can expect that in the near future, A1 will be accessed and A2 will be accessed, right? And then how the array data is located in the memory. So we learn, right? So the array is located in the memory like this. So A0, A1, A2. So once a certain data is accessed, then the neighbor data will be accessed the near future. So this is called the spatial locality. Then in our applications, data locality. So these are data locality. Temporal locality and spatial locality is observed frequently. So what does that mean? We can observe locality of data, which means a certain data is accessed, then this data will be accessed again. Also, the near data, the neighbor data will be accessed. So which means, when our application is accessing a certain data, then we can expect that same data, what neighbor data will be accessed frequently, right? So this is I said that this is the main approach for improving the performance of memory system. So frequently accessed data can be stored in the best memory. And then we can predict the frequently accessed data like using the temporal locality and spatial locality. Right? So if the frequently accessed data can be found in the best memory, then we can improve the performance, right? So we use the memory hierarchy. So I said that the best memory is small, right? Then, but from entire data, so we can select the frequently used data by exploiting data locality, right? So we can store frequently used data in the small memory like cache, because cache is best. Then this data can be accessed again and again from the cache, from the best memory, right? If the data is here, then it will take a very long time because the DRAM, the main memory, is slow. But if the data is found in the cache, small memory, then we can access this data. So by doing this, we can improve the performance. So this is the idea of memory hierarchy. So memory hierarchy, as I mentioned, exploit the data locality. So data locality explains that we can expect the frequently used data, right? Because the data exhibits temporal locality and spatial locality in our application. Because we can predict the frequently accessed data, then we can store this data in the best memory, right? The best memory is located near process. Okay? But the size is small. So we can select a part of data, part of data, then this part of data can be stored in the smaller and best memory. So by doing this, we can improve the performance, right? So this is the idea of memory hierarchy. Okay, so even though the memory is very slow, like this gap, but using the memory hierarchy idea, we can store frequently accessed data in the fast memory, right? So we can improve the performance. Okay, this is the memory hierarchy memory. Then you can say that, oh, then we can just implement the fast and large memory, but it's not possible. This is the ideal case, but there is no ideal things in the real world. Okay, so if the memory size is large and the memory is slow. Okay? So, so uh, in the memory hierarchy, then we can, so a processor can find required data in the fast memory, or a processor cannot find the required data in the fast memory. There can be two cases, right? Because as I mentioned, the fast memory size is small, right? We cannot store entire data in the fast memory. That means, oh, we can find the required data in the fast memory, or we cannot find the required data in the fast memory. So we do not consider this architecture model, the process architecture model, right? So for example, in the data, if the instruction access data memory, then we just assume that the data is the request data. The request data is found in the data memory, right? 100% with 100%. But I explained about the memory hierarchy model, but size of the test memory is small, which means the request data can be found or cannot be found. There are two cases. There can be two cases, right? So if a required data is found in the fast and small memory, then this memory is called actually cache. Okay, so I will explain about the cache later. So if the data is found, this case is called the hit. And then if data is not found, this case is called the miss. Right? And then you can find that, oh, these terms are same to the branch prediction. Branch prediction hit, branch prediction miss. Right? Because there are two cases. So a processor can firstly access the test memory first. Because the slow memory is located, it's a part of the processor. It's also slow. So a processor firstly access the best small memory, right? Then these memories are like the caches are close to processors. So firstly access this best memory. Then there are two cases. The data can be found, then data cannot be found. Data is found, it's called the heap. Okay? So if in the branch predictor, if the prediction is correct, then it's heap. Right? And if the data is not found, then it's called the miss. Okay? You can find the hit and miss. So this is called the cache hit. Then this is called the cache misses. Cache miss, right? The prediction is the same. The prediction is correct. The prediction hit. One prediction is incorrect and prediction miss. Right. So there are two cases. So in the memory hierarchy, so there are two cases, a hit case and miss case. because we cannot store entire data in the best memory, right? So we can define hit ratio like the number of hits divided by number of total accesses. So which means, we can access cache in the best memory. Then the data can be found or not. So from the entire accesses, only the part of accesses are hits, right? And then, so we can define the hit ratio. Hit ratio is the number of hits divided by number of total accesses. So what does that mean? If the hit ratio is high, which means, the required data are frequently found in the best memory. So which means the performance can be higher, right? Because the more data can be found in the best memory, right? This is cool. So using the hit ratio of cache, and we can expect, just expect the performance of a computer system. So which means enough to improve the performance of a computer system, then we need to improve the hit ratio. Hit ratio of is cache, best memory. So then we can also define the miss ratio, so the number of misses divided by total accesses. Okay, again, so there are only two cases: a hit or misses. Then the miss ratio is the 1 minus the hit ratio. Okay. So I explained about the hit and miss, the memory hierarchy. Okay, so this is some basic of memory hierarchy. And I briefly explain about the memory technology. Then why do we use the memory hierarchy? And then why a certain memory is fast and then a certain memory is slow? Because we can use the different memory technologies. Okay, so actually, in the software model just think that the memory is the same, but it's not true actually. So based on the memory technologies, the performance is also different. So static RAM, like it's called the SRAM. So this is the kind of fastest memory, the best memory, but it's expensive. It means the cost is high. Dynamic RAM is called the DRAM. So this is the main memory of the system. So you can find that the performance is lower than the SRAM, but the cost is also lower. So it's cheaper than SRAM. So this number, you can find that this number here, this number represents the latency of memory. What does it mean? What is the latency? The latency is that, so if we just give address to the memory, then we can get data, right? But memory is hardware, so after delta t, the delay. So this number represents this delay. Okay, then this is the latency of memory. So you can just compare the latency of memory here. SRAM is very fast. The latency is low, but this is the cost. Cost is high. DRAM, you can find that the latency is higher, which means the performance is low, right? But the cost is cheaper. Magnetic disk, as a hard disk drive, you can find that, oh, latency unit is the millisecond. What does that mean? So kind of tens of millisecond, extremely slow compared to the nanosecond. It's extremely slow. So that's why currently we frequently use the SSD because the flash memory is much faster than the hard disk drive. Okay? But the cost is low, the hard disk drive. Okay? So the problem is that we cannot use this expensive memory for the large memory, right? This is the cost issue. Also, so if we just increase the size of the memory, then the latency is also increased. So SRAM is the same. If we just increase the size of the SRAM, then latency is also increased. So that's the problem. So ideal memory is the access time of the SRAM, then capacity and cost of the hard disk drive. But this is just ideal. Okay, it's not real memory. Okay? So that's why we use the memory hierarchy. Okay, so I will explain about the basic fundamental knowledge of the memory data. So okay, so I stop here. Any question? And see you in the next class.